problems, one Neumann cure, and stable approximate evaluation of unbounded operators.
I have to thank the organizers for inviting me, but I really think they did it because I paid for the pizza. I can't think of anything that didn't I? Spike doesn't know this yet. I don't get the bill. Okay. Back in the 1930s, there was a very popular adventure novel in the United States, The Adventures of Haji Baba of Isfahan. I don't know, have you ever heard of that one? It was written by James Murray, who in the early 19th century was a British ambassador to the court of the Shah in Persia. And it's about a very bright young kid whose name is Haji Baba. He was a barber's assistant. He was captured by slave traders and went through all sorts of adventures. And in particular, he was sold into the house of the Shah. And there's lots of these funny sort of stories, you know, like the Arabian Nights type things, you know, things that went on in the court of the Shah. But one of the things that went on was there was a French doctor who came and stayed at the court for some time, and he was quite a charlatan. But he would convince everyone, no matter what was wrong with him, he had these little tiny white pills, and if you took the pill, he would convince you you're okay. And in particular, one of the Shah's ministers, who was in his mid-90s and who was preparing to die, was preparing his will and so forth, making sure that all of his 26 wives or whatever it is were taken care of. This doctor convinced him if he took the pills, he would get new vitality. And sure enough, he married a 20-year-old young girl, and things were great. So the Shah came to Haji Baba, was really puzzled by this. Can you explain to me why such great effects should come from these little causes? By the way, I think those pills are now patented by Pfizer. You see it on TV every night. You can't miss it. Anyway, that's what I'm going to talk about. Well, not really. Talking about the problem instability. You know, how can you have these huge, instances where huge effects come from very, very tiny causes? What I want to do is just give sort of a flavor of an area of approximation theory for unbounded linear operators that grew out of work that I was doing on inverse problems. So let me just give you an example of a classical sort of model inverse problem. Here's the standard one-dimensional heat equation, non-dimensional, all the parameters taken to be one, basically. It's the sort of problem that everybody does in a class, a junior level class in introduction to PDEs. You solve the problem by separation of variables. And in class, what you do is you start with some initial temperature distribution. Think of this as a bar stretching from 0 to pi, just for convenience. And you start with some initial temperature distribution, and you ask the students to find out the temperature at some later time. For example, at time equal 1. Okay, that's the classical direct problem, and everybody solves that problem when they're an undergraduate. The inverse problem is going backwards in time. That is, you suppose that you know the temperature at some time, and then you'd like to move back, travel back in time to find the initial temperature. Okay, and they're both the same problem. You just solve them by separation of variables. But what you find in this case is if f was the temperature distribution at some later time, then the initial temperature distribution is given by an expression of that type. You do it just by separation of variables. Let's call this operator that maps the temperature distribution at some time back to the initial temperature distribution, L. It's a linear operator. But you see something, you see the little white pills here, don't you? There's the pills, okay? What's the case? Well, a couple of things. Certainly, let's say we're working in L2 space, for example. This is not going to make sense unless this function f is some L2 function for which these quantities decay very, very rapidly, because they have to decay rapidly, or else what's going to happen? You've got these factors e to the n squared, which are going to be blowing up incredibly fast, okay? So L is not defined on all of L2, it's defined on only very, very smooth functions. You need functions whose Fourier components decay extremely rapidly so that this series here will actually converge. This has to be a little L2 sequence for this to make sense. The other thing is this, even if this is the case, if you perturb f, oops, sorry, let's go back. If you perturb f even by a small amount, these factors, the e to the n squared factors, are going to blow that up. So if you've got any sort of noise in the temperature distribution that you've measured that you want it back to the initial temperature distribution, it's going to be hopeless, okay? It's a classical unstable problem in inverse heat theory. So I want to think of that as the model problem. There are lots of other problems of this type. Cauchy problem for Clauss equation in the strip, Dirichlet-Neumann map, potential theory, in moment theory, in heat conduction theory. There's lots of such problems which lead to this same sort of phenomenon. Okay. So here's the general situation. What you want to do with one of these operators is evaluate the operator at some vector x. This x, of course, has to be in the domain of the operator, which means it has to be a very special x, but you never have that special x in real situations, right? If you're measuring something, you're going to have measurement errors, okay? So what you do have, instead of x, is you have some x delta, let's say, some rough measured version of f. And you have some estimate of how much error is in that measured version of x. And you'd like to use this x delta in order to approximate L of x. So you're going to approximate it by taking this x delta, which is available, and applying some sort of operator to it. Okay? Now, what sort of operator would you like to apply to it? Well, you'd like to apply a bounded operator, not an unbounded operator, because if the operator is bounded, then perturbations in your measurements are not going to have a bad effect on the evaluation process. I get confused as to which is in which hand. Okay, so you like these operators S of alpha. Alpha is just a parameter here. We call it a stability parameter, to be bounded. And you'd like to have them have the property that if you choose the stability parameter properly, in terms of the bound for the error in your measurements, so that as these errors go to zero, as your approximations get better and better, you'd like these things, all of which are stable, to converge to L of x, where L of x was the unstable operator. So that's the problem of stable evaluation of an unbounded operator. There's an old theorem of von Neumann that goes back to 1932 in the Annals of Math, which I've used to sort of give a general sort of description of this idea. It deals with this. You've got a closed, densely defined linear operator L acting on some dense subspace of a Hilbert space H1 going to another Hilbert space perhaps. And then this is my term, resolvent. It's some sort of inverse, so I call it a resolvent. Von Neumann looked at this operator here, and he proved this theorem back in published this theorem back in 1932 in the Annals of Mathematics. The theorem says that L tilde, this operator which is defined in this way, as well as L operating on L tilde, are both defined on all of H1, the original space, They're everywhere defined and they're bound. And moreover, L tilde is self-adjoint. If you look at von Neumann's original paper, he really thought this was something because he follows these two statements that L tilde is defined everywhere and L tilde is bounded by exclamation points. This was hot stuff. Anyway, so how can we use this to sort of give a general framework for this problem of stable evaluation? Well, here's the idea. You say, well, what we're after is L of x, and just formally we'll write it like so, okay? Of course, this L tilde inverse is an unbounded operator. But according to von Neumann's theorem, this operator here, L tilde, is a bounded operator. This is where the instability will come in right here. So by the way, I should mention that L tilde, the spectrum of L tilde is between 0 and 1, which you can see easily. Replace this part with some functional of the bounded operator L tilde, given in terms of some continuous functions on 0, 1, parameterized by some parameter alpha, which I'll take bigger than 0. Okay. So this makes perfect sense. This is a bounded operator by von Neumann's theorem. This, for each given alpha, is also a bounded operator just by standard spectral theorem for bounded self-adjoint operators. Okay. So, what would you like? Well, you want this collection of functions, just real valued functions, to approximate the reciprocal function. So you'd like this to happen. Of course, the best you can hope for is for this to happen pointwise for each t strictly bigger than 0, of course. That's the only way this makes sense. And another requirement that's you simply need to make things go through is that this quantity is uniformly bounded, meaning uniformly bounded for all alpha. Okay. Then one can prove a theorem. Okay, the theorem is this. These are the stabilized approximations. Okay. There's the same approximations using the data which is not in the domain of L. Okay. And one can, using standard spectral theory, you can prove the following results. For every x in H1, this operator here, this is y alpha, except L has not yet been applied. Basically, it says it's an approximate identity. It goes to the identity operator pointwise on H1 as alpha goes to 0. If your vector x is in fact in the domain of L, then it does exactly what you'd like it to do, namely L of x alpha goes to L of x. Again, I have to point out that these y alphas are stable with respect to perturbations in x. That's the important point. On the other hand, if x is not in the domain of L, then the best, what do you want if you're doing numerical computations? If you can't possibly, if the thing you want to compute doesn't exist, right? If x is not in the domain of L, L of x makes no sense at all. What would you like your approximations to do? You'd like them to blow up in your face so that you know it's wrong, okay? And it does that. The norms go to infinity, so in particular there's even no weakly convergent subsequence. And weak convergence is what measurement theory is all based on. So none of your measurements are going to fool you and say, oh, this is working. It's going to say, forget it, it doesn't work. Okay? But of course, all of this is based on knowing exactly the vector x that you'd like to evaluate L on, if that's proper English. Okay? And that's never the case, as I've said. You have to take measurements. Whenever you take measurements, you're going to have roughness in your data. So the real problem is, what if you've got unclean data? What if all you have, you don't know x, all you have is some measurement of x delta. This measurement's not in the domain. You can't expect this function to be very smooth, okay? You can't expect it to be L2. That's a reasonable assumption. What do you do then? Well, here's the key. if you can bound this quantity here, this was the t that appeared in the general formulation before, capital T, by some function r of the stability parameter alpha, one can prove the following result, that these stable approximations using the measured data to the desired value of the unbounded operator converge where you'd like them to converge. Namely, they go to L of x as delta goes to 0 if this condition is satisfied as delta goes to 0. Again, it's not very complicated. It's just use of standard Hilbert space spectral theory. Okay. You can do more. You can, if you can get a what you might call a modulus, which is some upper bound, which will depend on some positive parameter nu, as well as on the stability parameter for this quantity here. Then one can prove, again, it's just spectral theory. Whoops, sorry. You can prove that if x is indeed in the domain of L, and if you assume what sort of a smoothness assumption, sometimes called a source condition, that L of x is in the range of a certain power of another operator. This is the operator. You see what this is? This is just L star tilde is what it is. It's just turning things around to go the other way. Okay. Then one can prove this result. So you get an order of convergence results for these things. But again, this is at this point it's still using the clean data, the exact vector that you want to evaluate the operator on. Now there's an old method that goes back to the 70s at least, a specific method of this type, which can be put into this framework if you take T alpha to be this. So when you put that into that general framework, what it says is that you have this sort of result. Okay. Again, these are bounded operators here, so that you've got stable approximations to this unbounded operator. It's sometimes called the Tikhonov-Morozov method from the late 60s, early 70s. And there are many other possibilities. That's not the only possibility. That's sort of a canonical example. Here's another possibility. If you choose Tn to be this. Now here I've written, instead of alpha, I've written n, because now we're thinking of n as being a positive integer. Okay. So our stability parameter is now an iteration number. The iteration goes like this. When you plug into that theorem and work it all out, it looks like this. Here alpha is a fixed positive number, less than 1, and it's the n which is changing. Okay, so you start with some approximation and you iterate in this way. And you can see what the advantage of this method is over this one from a computational point of view. If you're varying alpha here, each time you change alpha, you've got to compute a new inverse. So you've got to continually compute inverses as you're going along. Whereas here, since the alpha is fixed and the n is changing, you just do one inversion, a single inversion, and then you simply iterate using that inverse. Okay? So those are two sort of canonical methods. But one can prove a result. Here's a result. Again, under all the previous assumptions, assuming x is in the domain of L, and if you've got this source condition, and if you have data which is within delta of x, and if you choose the alpha to be the stability parameter to be a constant times that quantity, delta to the 2 over 2n plus 1, then you can derive a result of that type. So here are the stable approximations using the measured data. Here's what you really want, and you see what this says. It says that if you let nu go to 1, you could get as high as delta to the, what would it be, 2/3 power, okay, with the Tikhonov-Morozov method. That naturally raises a question, can you do any better? Well, in all the operators of the type that I look at that appear in classical mathematical physics, this L tilde happens to be a compact operator. So if you assume in addition that L tilde is compact, and if you assume that you can do better, now what's better? Well, what's better than big O is little o, you know, that this goes to 0 faster than delta to the 2/3 power is what that says. If that happens for all perturbations, which are less than delta from the true function, then one can prove this, that the vector on which you wish to evaluate L happens to be in the null space of L. Well, that's not hard to do, right? If the vector's in the null space of L, it's not too hard to find what L of that vector is. It's 0. It's trivial. In other words, you're working on a trivial problem. Okay. So in effect, you simply can't do better. You simply can't do better than delta to the 2/3. It's a brick wall for that method. By the way, well, let me, is pizza next? Yeah, so let me get through this. Let me just show you a simple model problem. Here's the problem. We've got this semi-infinite sort of homogeneous solid here and a gas over here. It'll remind you of problems that you do in elementary differential equations. We've got a heat source in the ambient here, F of T. It's some sort of temperature which depends on T, so it's increasing. And then you've got the standard heat equation working on this side, and the problem is this. In your elementary classes, you deal with a problem like this where F is simply a constant and G is a constant, or actually 1 perhaps, or a constant. That's Newton's law of cooling or heating, depending on how you look at it, okay? And with that, you can determine what the temperature at the interface is at later times. But here's a kind of an inverse problem. Suppose you don't know what the physical principle is that's acting on the surface. That is, you don't know the boundary condition. The boundary condition that you'd be interested in is some sort of condition on the temperature gradient. How you know? Suppose that the temperature gradient is given in this way, where this is a variable that you know. G is some function that you don't know. Okay. So the question becomes: can you determine this function? Determine the physics that's occurring at the surface by doing a measurement on the surface. And of course, the simplest measurement you can do is just you put a thermocouple on the surface and just measure the temperature history. So you put a thermometer there on the surface and see what the thermometer does. Knowing F, knowing this temperature history at the interface, can you determine G, the physical principle at the boundary? Okay. Well, so there it is in equations. You have the heat equation in the right-hand plane in the solid. You measure this and you know F, and what you'd like to do is determine what G looks like. Okay, what physical process is causing the thermal transfer of the surface? Well, you can work it out. You do some standard things, and you find out that this is so. So we know this. We're going to measure phi, and then we're going to try to determine values of G. So what operator we'll be looking at will be having to evaluate this operator. L at phi is the evaluation of this expression. Okay. So, well, in principle, we could do that. We get values for this, and for each such value, we'll plug in here, and that'll give us a value for G, and we'll have points on the graph of G, and we'll see what G looks like. That will tell us what's happening at the interface between the gas and the solid. By the way, you could do this for other geometries. I'm just thinking of the simplest case. Well, here's a little toy test example. These all work. If your G is just this parabola, and if F is this function, this is the heating regime that you're applying on the outside. The surface temperature is going to be, the history is going to be given in that way. That's all a fact, you just work it out. So if we use this test example to try to reconstruct the G, we're going to measure this fellow and try to reconstruct G using this equation. By the way, this K happens to be that. With other geometries, it's other things, but that's what K is. Okay? So one could look at this numerically. There's various ways you could do it. What I'll show you next is an approximation that we get by taking the phi values and replacing phi by a linear spline approximation on a certain mesh. Okay, that's going to give us piecewise constants here when we differentiate those piecewise linears. K is something we know, which is simple. You can actually compute those integrals exactly in closed form. Okay, and you get a big matrix problem, and you solve that. Okay, so there's what you get. And I'm trying to remember exactly what the parameters, what I used for the mesh size here. I think I used a mesh size of 1/100th. You're going basically from 0 to 2, so it's about 200 points on the spline. Plug it in, get a big 200 by 200 matrix, but you just apply that matrix to something, you bring it across, and then you compute G. And what I plotted there is the true G, and also I plotted the G that you get from using that numerical method. And you see them, well, they're the same. And you can't tell the difference. It works perfectly. Okay. But that's not the real problem. The real problem is what? When you take the measurements of the temperature on the surface, you don't really get the temperature on the surface. You get some approximation of the temperature on the surface because you've got numerical, you've got measurement errors. So you can go back and do the whole thing over again, but simply perturb the phi values. Okay? And here you get where I perturb the t values, the phi values, the temperature values at the surface by 2%, random error. And now you see the true solution, which is this, and the thing that results from this very tiny little white pill, the 2% noise that was put in. And you see the instability coming in. I like this because this is what we preach to our students about. The damn thing's not even a function. It doesn't pass the vertical line test. You see, because the phis are going into as the ordinates into the G, right? To plot the graph of the G. Well, they're going all over the place. Very small, big effects come from very small causes here, and that's of course what happens with an unstable problem. But if we go back and use TM, Tikhonov-Morozov, I happen to use that parameter. There's lots of issues here, but there's what you get. It's rerun now using the Tikhonov-Morozov method with that for alpha, and now you have the true solution and the computed solution, which is any engineer would be happy with that. Now, what I've done, if I haven't run over already, I've run over, haven't I? 2 minutes? I paid for the pizza. It's just a very slight sketch of a lot of work that I've been doing since the 90s. Original work in the 90s with a couple of collaborators, my friend Otmar at the University of Vienna and Martin Huck at the University of Mainz. Recently, I haven't done much on it because I've been otherwise engaged for a while. But I did put all the stuff together a few years ago in 2007. There's a lot more involved, but I just tried to give you some flavor of what the idea is for in this talk. So thank you. Let's have some pizza.
Was Von Neumann working on an applied problem?
This is the time when he was developing the quantity operator theory for quantum mechanics, and the whole idea of the unbounded operator was around. You can find, actually, you don't have to look at his original paper. The only book that I know that has that theorem, and it's the classical Riesnage.
Yeah, that's where I saw it seen.
Yeah.
I don't remember that.
Yeah, and it's all beautiful, it's all very Cartesian, you know, it's all graphs.
Yeah.
Graphs not that you look at, but graphs as ordered pairs, and you flip things around. It's good, very pretty stuff, very Flamonnish.